class from Toluca. If that works, you'll just be sitting in here watching a presentation and listening to my voice. If it doesn't work, you'll be sitting in the class listening to Larissa, right?
Yes.
So the plan is that you will get to experience a little bit of what all of the remote students are experiencing, hopefully good, but you'll get to kind of see what they are taking part with from this visit. Now, more than likely, it'll happen one more time in November. I will be down in Brazil working with the Sao Paulo students and trying to lecture from their back. Question?
You need an interpreter for your Mexico trip?
Do I need an interpreter? I'm sure that a number of you would volunteer. But no, I've been there many times. I don't speak Spanish, but I'm pretty confident I can survive.
You should just take your Toluca group with you. So.
I should. And the USP group. But I don't have that kind of money. So, all right. We're actually a lecture behind, and so I'm going to attempt to kind of make up ground today. And then on Thursday, if everything goes well, we'll get caught up with the lectures and where we're at. So we're going to spend a little bit more time today talking about topology optimization, kind of looking at a few more case studies. But at the end of the period, what we're going to try and focus on is the activity of lab this week, which is how do I take my topology result and get it back into a CAD system. And so we're going to talk about a little bit of research that has been done here at BYU, but we're going to also talk about how this is a very open-ended problem that in your career as an engineer, I am certain it will be solved, but right now it kind of still remains as kind of an open problem or an open issue. And so we're going to get into that. All right, so just a little bit of a review about topology optimization. What are the two general mathematical approaches used in doing topology optimization? What are the two approaches that we talked about? And if you don't know their name, at least describe what they are, how they work.
It's the one with the voids in the middle of the elements.
Okay, the one with the void in the middle of the element. Okay, how does that work?
You change the size of the void and therefore the density of the material.
Right, so if we can think of the void as being rectangular, which it doesn't have to be, but if we think about that, we can vary the length and width of that void in 2 dimensions. And we can, by doing that, change the density of the cell, the density of that finite element, and compute kind of the load paths, the stresses and strains in that type of an element. Okay, that's one approach. And is that a continuous approach or kind of a discrete approach? Did we refer to it as continuous or discrete? We refer to it as a continuous approach. Okay. What's the other approach? The other mathematical approach? Louder, Jeff. The one with the circles. So we have a defined void of some shape. The example was a circle. And what do we do with that? We drop it at every point in the finite element solution that has what? Low or no stress. Okay? Very low stress or no stress. And what do? A subtraction function. Okay? And so we just eat away in kind of a discrete way where all of the zero stress points are, and that gives us a topology optimization. Okay?
That one's discrete, right?
That was discrete. Okay? What is the difference between ESO and BESO? Are you guys reading these articles, hopefully? You're starting to?
ESO can only take away material and ESO can add material as well?
That is correct. So that's the main difference, is the ESO is strictly an eating away of the topology, but a BESO can actually add topology where you need it. Why do we do topology optimization? What was the kind of the motivating factor? Weight.
Is there material costs?
What's that?
Efficiency, money.
Save money. What else was saved? Time was saved. So on almost every example, they talked about weight reduction, and they talked about time reduction, okay?
Just a question about that. It seems like the geometry that you're going to be coming up is going to be a whole lot more complex, which might make the material go down, but wouldn't that make the manufacturing costs go up?
You have to look at that and decide, whether to do it with a casting process, to do it with a milling process. You have to decide kind of how complex. And we've got some examples that you'll see in this lecture where they looked at it and said, that's way too complex, we're going to simplify it. And by simplifying it, they still left in more weight than the optimals that they needed, but it was easier to manufacture by doing that. So there are trade-offs. What is today's main challenge with the implementation of topology optimization? If there's one challenge, what is it?
Communicating back with the CAD system.
It's getting it back into CAD. And that's kind of the crux of what the last half of our discussion is all about. Okay? So last time we talked about all of these other kind of methods. We didn't talk about the truss method. And so just very quickly, Mitchell, back in 1904, and I'm sure others in China probably also came up with it, and maybe even earlier than what Mitchell did. But Mitchell is basically the father for the United States of doing truss optimization. And so he went about saying, what is the problem? How do I kind of make it the lightest, simplest, easiest structure to work with based on the constraints? And so he knew where the loads were, he knew where the boundary conditions were, and he basically said, what truss structure is going to be able to support this? What cross-section of the truss am I going to use? And it was driven by trying to get the smallest, the fewest number of elements and the smallest cross-section of the truss to actually do that. And there is a paper that kind of, plenty of papers that talk about and reference the truss topology optimization. So hopefully by now you've at least looked, and I would hope have read the Boeing article, the airplane, aircraft landing optimization. It, in that paper, talks about kind of two different components that they're working with, and the optimization that was done to minimize the stress and also take out the weight of the plane. In that article, they set up a process of going from a design space to basically a topology optimization back into kind of geometry and then doing a size and shape optimization. So in this class, we don't kind of do this last step, the shape and size optimization, but it's available, and we will talk a little bit about it once we get into the finite element stress calculation of our actual parts. We will come back and say, okay, you have a parametric part. Can you improve the part by changing radii, by changing thickness? And that's where you get into the shape optimization piece. Should I kill the the lights. Would it be better to drop the lights? I'm a little leery of doing that because I see heads kind of nod off from time to time. But this is a Volkswagen case study. On the left, they started with the best design that they had to that point in their product line. So this is a bracket for an alternator air conditioner combination. So that's kind of the optimal original shape that they had been using for years and years and years. The thing weighed about 2,000 grams. They did a design space, which is the kind of the light pink color, the second image. They ran it through topology optimization, which gave them kind of the middle image. And then with that, they had to say, is that really what we want it to look like in our CAD? And so they had to go from this tessellated representation to something that was manufacturable. And notice the first thing that they brought in, all of these red dots, are what? Their non-design space. So they just sucked that in from their original design model. Their original model had in it some size hole attachment places that they just adopted into their final model. So they brought in the non-design space, and then they began modeling a shape that would be somewhat close to the tessellated optimization shape. Once they finished that shape, to close the loop, they had to do a normal, traditional finite element model. So they took this shape, loaded it, constrained it, put all of the kind of constraints on it, boundary conditions, and did a finite element analysis to look to see whether it was a good design. Once it was a good design, they came back and asked what was the actual weight of this part. Okay? Notice that they saved 450 grams on that. Here's another Volkswagen case study, the very first one, 218 grams for this bracket that attaches alternator and air conditioner. They did a design space. They did a topology optimization. Does this little I want to call it a singularity. Does this thin member here in the middle, does that look realistic? Does it look believable? You know, it may be that you find in your optimizations, you may find that it has approached eating everything away, but when you look at it, you start saying, wow, maybe I didn't account for all of the load conditions. Maybe there is a moment or a torque or something else that I need to be thinking about. And so the engineer, seeing this result, came back and noticed that he put two sides to this thing. He just left the center open on that part because his engineering intuition said, I think this is going to last longer, hold up, be more robust design than what the optimal suggests it ought to be. And so made a manufacturable part, did a finite element. So this week we are going from image 3 to image 4. We're going to be talking about how do we get this image 4 back into our CAD system. Another example, same kind of thing, a bracket. This was the best that they had, 258 grams, design space, topology optimization. This is their new design, okay, and a finite element. And they ended up saving, weight-wise, about 350 or something on that. So why did Volkswagen do it? Okay. Well, hopefully this kind of brownish tan circle helps us understand. First off, Volkswagen knew